Hey Abraham, how are you?
Hey, I'm doing pretty well.
How's your semester going? Good?
It's going well.
That's good. You're doing full time, right?
Yep.
Okay. I'm a little early than usual, but figure I pop in early so in case anyone has questions.
Mhm.
I got disconnected last week, twice. I tried to get on my other laptop and something happened to the bandwidth, so
Uh,
yeah. Go ahead and download this week material if you haven't done that, so that way we can get started in about 7 minutes. Okay. Hi. Everybody start to log in now, so let me put in chat. If you guys want to download this week material, oh, so we'll start in about 4 minutes. If we can download assignments and notes for your class, I have updated grades. We'll talk about what we also have to do as homework this week. Sorry about last week. I got cut off because my connection was unstable. I tried to get on a couple of times and then Zoom boot me out. Somehow it just brought me to my own room and then I couldn't see everyone. So yeah, we're programming in set and C++ this week. Oh, is it empty? Let me double check, okay? Oh, because it's not activated till tomorrow, Sal. You will be able to download it tomorrow. Sorry. I had originally set it the day before class, so that way, you know, we'll get through the assignment today and then tomorrow you can download the lab. Any questions before we start? No questions. So we're moving along. Seems like pretty okay. So if you have questions and you don't want to ask during class, you can always pop in my office hours or shoot me an email. We'll wait another minute and then I'll start in a minute.
Professor, are we going to do the quiz review today?
I'm sorry, repeat your question.
Are we going to do the quiz review today?
No, that is a homework assignment. I intend to go over that shortly. So the homework assignment is designed as a study guide for you to prepare for our quiz next week. It's not going to happen this week. So next week you have a quiz. And that's going to cover all the chapters we've gone through in the first 3 weeks. So if you use that and go over the questions, you should be prepared for the quiz. Did everybody have a good Labor Day weekend? Albert also asked in chat. So mine was okay. I had to go look for another refrigerator. COVID makes things a little difficult, but you know, besides the heat and the fire, it was okay. I hope yours were fine. Okay, so I'm gonna go ahead and get started at 6 o'clock. Welcome back to CIS7. I'm glad you can join me in the session today. So today we're going to talk about the next module, which is going to be our Unit 3. We are going over sets, and we'll talk about Venn diagram. We'll talk about what consists of a set, how to do set builder notation. And then on Thursday, we will touch on how to program in C++ with set STL. So we'll talk about the container a little bit today, tie that into the math concept. And then on Thursday, you experiment more with creating the program that's going to include sets. So I'm going to go ahead and get into share screen. If you have any questions, please unmute and ask. And I will post the video as soon as I can, when I can get YouTube to caption everything. What happened to my, there's my class. Okay, so just side note, there's a homework assignment that's in the homework grade category. Make sure that you look this over and complete it by next week. I had set it for the 15th. I do things a little different this semester, giving student a little bit more extra time, because when I got the survey that I created from the last semester, some students, they struggle with absorbing the material and getting things in. I understand you have a lot of different assignments for other classes. So this is a study guide. It's intended to be used as a study guide. So as you go through the quiz review, you will find the materials that's going to prepare you for the next quiz, which is going to be in week 4 or in unit 4. I will do a little fun game for some e-gift cards next week as well. So as you go through the assignment, it's going to help you prepare for the quiz and also the quiz game. Today, right now, we're going to cover the notes and we are going over the assignment together as, as a group. So in chapter 7, we're going to skip some of the chapters and we're going to come back to those. I know we left off with like 2 and 3. So we're going to come back to chapter 5 and some of the other concepts. So in chapter 7, it begins with talking about sets. And as you know, if you have explored C++, created program that has sets, you can use set STL, which we will touch on Thursday. But in general, we can even create a container or an object that would hold values, and as long as they are individually unique. So for example, we can have an array and we can have integers initialized as each element for that array. Or we can even use vector. The benefit of using vector is that it will grow, right? You don't have to set a size to the number of elements would be compared to array. So vector is definitely more flexible. You can also use dynamic array. Now, set as an STL in C++ is a little bit different, where you can utilize member function to change the content of that set, but not the individual value itself. So let's talk about set from a discrete math perspective. It is an unordered collection of objects or elements. Now in C++, compare that from the math concept is that in C++, the way they wrote the STL for set is that it has a weak ordering, meaning that it does have a pre-sort. So a set could be a collection of anything from numbers, right? You can have whole numbers, or it could be characters like A, B, C, D, E, F, G, etc. It could be a group of objects, but in an unordered manner. So it's a collection, and we would treat individual entity in this collection as element. So to start, we would have natural numbers, and you would see natural numbers would be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? Could be integers, okay? Then you would have Z to represent integers, and that could be negative or positive numbers. And if you are looking at only sign integer, like in C++, we would say unsigned int and sign int. So if we say sign int, that means that it's negative integers. And then if we say unsigned int, that will be positive integers. And then on the next one, it talks about rational numbers, and that can represent as fractions. So you would have P over Q, like 5 over 4 or 1 over 8, right? And where Q cannot be 0. Then we would have real numbers, and real numbers would include rational and irrational numbers. So it would be, we would look at sets and its subsets, or a set could be a subset of something that's greater, like natural number or real numbers. And the way that we write our set, similarly to what you would see with a collection of values in programming, you would use the curly brace to enclose the elements. So on this last line here, it says that set S would have value 1, 2, 3. So there are 3 elements or 3 numbers that's contained in that set. So we would use the curly brackets or the curly braces to represent the set and the elements within that set. So going further down, it tells you that you can have different things in your set. You can have letters in C++, that will be char or characters. Or we can have 0 and 1's values. And in the example here, it shows nibbles, which is 4 bits for each element. Or we could have different type of phrase or even word could be represented as string in C++. So as a set basic, we can say that an element could be part of a set. So let's say that X is an element of S, and S is our set. Then we would write X, E, S. That means that X is an element, it's in set S, okay? Now, when it's not, you would simply use the E with the slash to say that it's not an element or it's not in S, okay? Now, sometimes you would come across sets that are equal. Remember that this is a collection that's not ordered, it's unordered. So that means that it could be in any order, as long as it has the same value, then it would be the same. So for example, we would have A, B, C would be equal to B, C, A, that will be equal to C, B, A. Okay? Now, later on, we're going to get into a different concept where we talk about permutation, where order does matter. That's a little different. But for now, what we're looking at is a collection. As long as it holds the same number of elements and the elements' value are exactly the same, then they are equal. So in the case that we look at so far, like ABC, BCA, and CBA, we know that this it contains finite number of elements, like 3 elements in that case. So in a finite set, you can determine the cardinality or the size of that set. And when we're looking at something in programming like C++, we know that if we include the array STL, we would see that we can use size of to really determine the length of that array, or the length of is really determining the number of elements in that array. So cardinality, just technically, it just means that it is the number of elements or the size of that set, okay? And the way that we denote that is that we would use the pipe symbol on both sides. So when you see this, you would know that the question wants the cardinality of that set. So you simply count up the elements inside that set. So for example, we have set S and we have 1, 2, 5, 7. These are the values in that set. So its cardinality is 4 because there are 4 elements in that set. So in the finite set, we can simply count up the number of elements in that set, where if it's infinitely containing so many elements, right, there's infinite number of elements in a set, and that could be possible, okay? So the cardinality of the infinite set is that it is infinite. Now, on the next part, it talks about how it can contain no elements. And you do see this, right? We see this from the programming side, is that I'm going to use the array again, where you don't have to initialize the element values in the array. You can say that technically we can have the size to set, but we don't have to assign it a value yet. Or in a vector, what we can say is that, okay, well, this vector right now is empty, but then we would add some of the elements as we go. So you do see some of this from the programming side, but on the array, it's a little bit more strict, where the rule of the array is that we have to tell the compiler that my array contains this many elements, even though we don't initialize it. And so when you initialize it, it's going to place it into the index. Now, when we declare the set with the variable, the computing, sometimes we can just have it as an empty set. So in the case of an empty set, we would use just the set of the curly brackets or a 0 with a slash through. Okay. So I'm going to pause there. I'm going to go to our assignment, and then I'm going to help you answer some of these questions. So what I did was I made a little chart. These are just like little charts, so you can use the symbol. You can simply copy and paste this when you do the set builder notation, right? Or you can simply, like this one, you can write it as a capital E, but for some of the other symbol, you can simply copy and paste it. So in the first question, it asks you to denote A as an element of B. So we can simply say A, right, and use the E symbol, and then B. So what that's saying is that A is part of the B set. And A could be anything, right? It could contain a value, it could contain a character, it could be anything. So A is an element of B, and that's how we would denote it. So for your quiz and your test, I would expect you to be able to interpret the set builder notation. So when it gives you something like this, you would know what it means. Any questions so far? Okay, and we would continue similarly to number 1. Number 2, it says denote V as an element of T. So again, we would say V and then ET. It is an element of T. Pretty simple so far. Any question? Then for 3, it asks you to denote the cardinality of P, where P is 4, 9, 24, 60, and 105. So we simply count up the number of elements in that. So we have 1, 2, 3, 4, 5. So we know that that set contained 5 elements. We can simply state that the cardinality of P, so you can use the pipe and then type in the set name, which is P, and then close that. So that would be the cardinality of P is 5. For number 4, it asks you to denote the cardinality of Q, where Q is 1, 16, 28, 67, 90, 111, 134, 254, and 314. So if we count up the elements for set Q, we would have 1, 2, 3, 4, 5, 6, 7, 8, 9. So we know that there are 9 elements in set Q. So we would denote the cardinality is 9. Any question? And as we left off with our notes just a few minutes ago, we talked about how it could be an empty set. So you would denote an empty set F using the F and a set of curly brackets, or you can say F0 with the slash through. And that's how you would denote that F is an empty set. Now that we know, technically, when we look at container to start is a way that we can set up a size in a memory, a space that could be reserved to store value. So if you think about that, we would start with an empty container to start, and then we would give it assigned value. Now, depending on the type of container or the object, but in the next part of the note, we're going to touch on how the sets are compared, right? Where do you start? And you always should start with an empty set, and then after that, we would put in one element, two element, and so forth. So that way we would have our set. And remember, set, right, for C++ is that it's unique. So when you have repetition of number, the way we write it out, we don't rewrite the repeated number. So if I have, for example, 2 of the number 1, it's only going to be written once, okay, for set, because they have to be unique. Any question? So for 6 asks you to determine if x is equal to y, and set x is given 11, 99, 44, 33, 77. Y is 99, 77, 33, 44, 11. Explain your answers. So when you see a problem like this, the first thing that you need to do is to compare the cardinality of both sets. If you have more than 2 sets, you need to compare the cardinality across all the sets. So when you're looking at set X, the cardinality of X contains 5 elements. Okay? So 11, 99, 44, 33, and 77, 5 elements. Then next, we would look at Y. The Y set also contains 5 elements. Okay? So since they have the same cardinality, then we would see if the values are matching, are the same. Okay? They both have 11. They both have 99. They both have 33. They both have 44. And they both have 77. So they exactly match. That means that they are equal. So the answer would be that X is equal to Y because they can contain the same elements and have same cardinality. In some cases, you would see that they would contain the same values, but one set would have more elements than other. Then they're not equal. Any question with any of the questions, the problem we went over?
Professor, could we see an example with the C?
Where they're not the same? So let's say that if I have Z, And if Z is equal to 11,
Oh, no. It was a C in the table.
I'm sorry, you're cutting out. Can you repeat the question?
It was a C in the table that you had.
Up here? The complement?
The complement. Yeah.
Yeah, we'll touch on the complement down the line. I'll do an example with you with the complement. We'll do one, okay? Because we
Right,
would look at the set and how the differences across the set. That's when we're going to look at complements. Okay. So
Okay.
we'll come to it. Hold on. Okay. All right. Anything on 6? Okay, so now we're going to compare additional set. So we have 7. It says determine if A is equal to B and C when A is -2, 55, 23, 91, 67, 82, and 10. And B is 67, -2, 82, 55, 10, and 91. And C is 23, 91, 10, -2, 67, 4, and 55. Okay. So what do? The first thing we need to determine is the cardinality comparison. So we have to see, okay, how many elements is in A, how many elements is in B, and how many elements is in C. So for A, we have 1, 2, 3, 4, 5, 6, 7 elements. So the cardinality for A is 7. For B, we have 1, 2, 3, 4, 5, 6. So B has 6 for cardinality. And C, it has 1, 2, 3, 4, 5, 6, 7. It also has 7 elements. Okay. So we know right off the bat that A cannot be equal to B because they're in different size or they have different cardinality. But we also need to compare A and C. Okay, so then what you do is you check the values for the elements to see if they match up. So we know that they both have -2, they both have -55, they both have 23, they both have 91, right? They both have 67. But when you get to 82, for A, that's different compared to C because C doesn't have 82. Okay? It has 4 instead. And then they both have 55. So it is not equal because it contains different value. A contains different value compared to C for that element, even though they have the same cardinality. So we know that B cannot be equal to C because B has less elements than C. So therefore we can conclude that A is not equal to B, is not equal to C, because A contains more element than B. I should put a period there. And C contains different element than A and B. Any question with number 7? So you will be given something similar to this for quiz and exam, your final exam. You will be asked to compare the sets. Could be 3, 2, 4, many sets. And what you have to determine is if they're equal or they're not equal. So to recap that, we just simply start with comparing the cardinality of the sets. And if they're exactly the same cardinality, then we start looking at the values inside the element values inside that set. Any question? Okay, if you don't know, you don't understand something, make sure you stop me and ask. Okay, so next, we're going to talk about putting it into set builder notation with the equations. So in this example, what it's saying is that x is an element of real numbers, and given that x squared plus 4x plus c is equal to 0. So technically, when we go through this, we can plug in numbers, right? We can start with the 0. That's where you would start. Then if we calculate it, we would have, so when you have x is equal to 0, you would get the f of x, or the result of that equation would be -4. And then when you plug in 4, you get -2 and so forth, okay? So now all we have to do in the next part is to write it out with set builder notation. So first, we need to identify the variable. Like in this case, that will be v. In the last case, that would be x. And we would use the pipe and state the condition on that variable. So for example, right, it would say here, v is an element of S. So you know that S is the set and v is part of that set. Okay. Then we would state the condition on v. So we can include the equations, or sometime it would be that v is greater than a certain value, or v squared is equal to a value. Okay, so that condition needs to be stated. So let's go down a little bit further here, and we would look at this example. So it's saying here in this example 7.2.1 that x is an element of z, right, integers, and absolute value of x is less than 5. So it means that the set of x in z such that absolute value of x is less than 5. That's what it means when we're reading this. Okay, so what could it possibly be? These values, because when you plug them in, right, absolute value for x, so if I plug in -4 for x, it's less than 5, because -4, absolute value of -4 is 4, and it is less than 5. So it could be these values. Okay. Another way that we can write this is x is an element of z, which is integers, right? Absolute value of x is less than 5. Okay. So as you can see, what we need to do is first we need to say what is it a part of, what is it an element of. Then we would state the condition of that variable. Okay, like x squared is less than 10. And in such case, that would be -3, -2, -1, and so forth. Okay. Any question with looking at this example, something you're not clear on?
The absolute value, we wouldn't use it as cardinality in this sense then?
No. In the condition, you just simply use the math notation for that. Yeah, only in set builder notation. So when you do an absolute value of the set name, then we would, or we put the pipe around the set name, then we would say that that is a cardinality. Okay. I know it's confusing that they're using the same symbol, right? But when you say cardinality, we know how to notate it. That we would use the set name, put the 2 pipe around it, and then equal to the number of elements. Where in this case, this is part of, think of it like the equation, right? That's the equation that variable is part of. So this is how you would state the equation following for the condition of that variable. So let's look at the next one, number 8. So it says provided the set builder notation for the following. The set of R in T such that R is greater than 7 and the set is 3, 7, 10, 14, 17, etc. So what we have is we have a larger set that contains those values 3, 7, 10, 14, 17. And then within that set, we have a subset. We have a subset that is R, and R represent that subset. So R needs to be greater than 7. So when we're looking at those values, we can say that R needs to be 10, 14, 17, because 7 is equal to 7 and 3 is less than 7. So we would start the set builder notation with R is an element of T, because T is that larger set. Then R is the subset. That's what it says right here. R is in T. That's what we state right here. That's the first part. Then we would have R is greater than 7, because that's the condition that we need to state here. That's the second part. R is greater than 7. Where R is, and logically from here we can say that it needs to be 10 and higher. So 10, 14, 17, because it needs to be higher than 7, and the next number after 7 is 10. So 10, 14, 17, and it can go infinitely. Okay. So any question for 8A? Okay. For B, it says that the set of integers such that y to the third is greater than 7, and the set is here. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay. So we would have y is an element of integers, and the way that we notate integers is with the capital Z. So we took care of this part. It is part of the integer set. And y to the third is greater than 7. That's the condition. Okay. So if I plug 4 in, 4 to the third, right, that's greater than 7, 5 to the third, that's greater than 7, and so forth. Any question would be?
Why is it we don't have to include the set for B, but we have to include the set for A?
You can include the set for B. It's just they're the same because in the A, we eliminated the first two because those two didn't meet the condition. That's why I added it. But, you know, for the set builder notation, this is all you need. But you know that the values needs to be, it needs to meet the condition. I'm getting a little lag, so hopefully I don't, there I go back again. Okay, good. I didn't lose Zoom. So yes, you can restate this. Copy and paste it over. You can say, you know, where y is equal to, and then your set. Oops. I had my YouTube on my clipboard. There you go. So if I have y to the third, right, 4 to the third power, it's greater than 7, of course. So any of those numbers would meet the condition. Okay. Let's do C. I'm going to move this down to the next page so we see it together. So for C, it says the set of natural numbers such that y squared is less than 100. So we would start with the first part of the statement, set of the natural numbers. So y is an element of natural numbers, n. Then we state the condition, and they gave us the condition here. Y squared is less than 100. Now, if you want, again, you can state y is equal to, given the set value 3, 4, 5, 6, 7, 8, 9, because if you squared 3, that's less than 100, right? So we met the criteria with all the set values. So what I want for you to know how to do in this exercise is to make sure you know how to use the set builder notation. Taking the statement, interpreting it, and putting it in using the notation. Okay? And this is another format. So you can do it one way, you can do it the other way. However, you know, that would work too. I like this way more because I can simplify it, you know, versus adding additionally more details to that. But this is another way. So for D, it says the set of S such that S is equal to 9y, where y is the natural number. And the values are 1, 3, 5, 7, 9, and so forth, all the positive odd integers. So we can say that we can start with the condition first here. we can say that S is equal to 9y. Then that only specify S. And then Y is an element of natural number. That's the second part here. Okay. Now for another way we can do is we can say Y is an element of natural number and S is equal to 9y. So however you write that, it's still going to mean the same thing.
How is it we specify that it's a positive odd integer for this?
So let's Y equal to 1. Let's try that, right? 1 times 9 is going to give you 9. It is definitely a positive odd result. Okay, 3, that's going to work too. 5, so technically you can specify that you can include this. Where's the positive odd integer? So you just have to include this part because it can infinitely go. Okay, because what it's saying here is all of this is going to be equal to anything that's going to be positive odd integer. So if you take 9 times y, where y is any of those value, you're still going to get a positive odd integer.
So we would have to include the set then, right? In order to write this out?
Yeah. Yes.
And how would we include the set if we were to use the second notation? Would it be the same way as the other ones?
Yes, comma, y is this. Because with those values, you still meet the condition that it asks for, right? Because if you take 1 times 9, 3 times 9, 5 times 9, 7 times 9, and 9 times 9, you still have a positive odd output. So for the test, you will be given more of like the first part like this. So something like this, it would say that a set of the natural numbers such that, let's say y cubed is less than 1,000 equal this set. Then it's going to ask you to select the following option that would be the set builder for that statement. Okay? But when you see this now, you would be able to see, you would be able to interpret that and say, okay, that's what it means. This is the condition, and this is the set, and this is the element. Any question? So before we start going into drawing that diagram, let's talk about Venn diagram. And this ties with set. So as you see, that natural number is the larger set, and that can represent the universe, right? On the scale of humans, we can say that, let's say that you're a college student, right? So the universe can be students in general, students in the world, okay? And then we can have a subset that will be Moreno Valley College student. That's part of the universe, okay? So you're a Moreno Valley College student or RCC student, so you're a subset of the larger set, which is the world student. So, the universe can represent the greater set, like real numbers, everyone in the world, And then we can have subset to specify a certain population, a certain collection of data. Okay. So here, this S right here can represent the students in Inland Empire, where the universe will be the students in the world. Or the universe would be all natural numbers, and then the S would contain specific numbers. So this is how you can use Venn diagram to illustrate sets and subsets. In some cases, you would have two disjointed sets. Okay. We can have one population and then another population, but it's part of the universe. So we can say A can represent female students, B can represent male students, and then the universe will be the world of students. Students in the world. Okay. So this one is disjointed. Now we can say, in some cases you would have that they are joined together. Okay. But let's look at this real quick. It says that we say that A is a subset of B, then A is included in B, and B includes in A. For that, every element of A is also an element of B. Okay. So if you're saying that if I am part of that family, then the people in that family would be, they are family members to me, and I am family members to them. Okay. Now, the way that we notate the subset would be like this. A is a subset of B, and B is a subset of A. Okay. Now, if they are equal, meaning that the elements are the same, then you would put the line underneath. Now, if we say A is a subset of B, but A has different elements, then you don't put the line underneath. That means that it's not equal. Okay. So going back to the earlier questions when we're looking at the comparison of the sets, where they have some of the elements, right? But they have some different elements. So in such case, you can see that there is a subset pattern that's happening, but they do, like one, like set B would be larger. So that means that they're not equal, but they do have same value for some of the elements. Okay, so we'll get into the union and the intersection shortly. But Venn diagram is a good way to graphically illustrate how sets and the relationship between one set and another set and how that is part of the universe. Okay. So all of this actually pointed to this diagram, okay? So A is a subset of B, and B is part of the universe. So they're both part of the universe, but we can say that. So think about, like, let's look at it this way. Think about like family structure, like your family tree, right? Your immediate family is like this group right here, A. And then your larger family, like your cousins, your uncle, your aunt, is the group B, where your parents are part of, you know, their siblings and so forth. Okay. And then as a population overall, right, is the universe. So your small family is part of the greater family, and that family is part of the larger population. Okay. So that's a way that we can represent a proper subset. So going back to question 9, it asks you to draw a Venn diagram that contains two disjointed sets, P and Q, with elements from the universe U. So the way, I don't know if you're familiar with adding shapes in Word, but I'm just going to show you for those of you who are not familiar with using shapes. Okay. If you want to draw this, right, of course you can use other tools, but if you're using Microsoft Word already, you simply do insert. And then on your ribbon, there's a shape button. You can click it. And then first we need to draw the universe. So select the rectangle and then drag it. And you can color it any way you want. Right? So again, insert, shape, and then choose the shape that you want. I start with the rectangle so I can label it universe. So click that and then drag. Now to add text, you simply right click and then choose add text. Okay. So here, if you want, you can just put in U, and then we can make this a little larger so we can draw like, you know, our little circle. And again, insert, shape, we can draw the little round. And then if you want to color, you can choose the color. And then add text. I have P. And then I can draw another one. So when they're disjointed, that the two subsets are separate. So we have P and Q as separate circle. Okay. So for our test and quiz, you need to be able to interpret Venn diagram. Like it would show something like this, and it asks you, are the two subsets disjointed or other criteria? So you select the appropriate options for it. Okay, let's look at 10. Do you have any question on 9 on how to draw this? Okay, let's look at 10. So question 10 asks you to determine if the statement is true or false. First one. It says if R is a subset of S, then and R is included in S, or S includes in R, then every element of R is also an element of S. Okay. So R is part of S. R is included in S. Just the same, the first two statements are the same, right? Or S includes R. Then every element of R is also an element of S. So it's like saying that my family is your family and your family is my family. Then everybody in your family and my family, they're family members. So true. For B, it says every element of G is an element of H, but there is at least one element of H that is not an element of G. we conclude that G is not a proper subset of H. False. It still can be a subset with the difference of one element or more. So every element of G is an element of H. So for example, that would be like this. Let's say that we have G is equal to 1, 2, 3, 4, let's say, okay? But there's at least one element of H that is not an element of G. So H could be 1, 2, 3, and 5. So when we can conclude that G is not a proper subset of H, well, you have the same elements here that should be overlapping. Okay. Or in some cases, we would have 4 and then 5 like this. So we can say that G is a proper subset of H, in the difference that H has an extra element. Any question with A or B? Okay. For 10C, it says if X is a subset of Y, but X is not equal to Y, we saw that yes, you can have subset and it doesn't have to be equal. It can, but it doesn't always have to be equal. So X is a subset of Y, but X is not equal to Y. And same example, right? We can say that, let's say that X contains 1, 2, 3, 4, 5, right? And then Y has higher cardinality. 1, 2, 3, 6. Doesn't have to be equal. Now, in the case if it has the same exact value, sure, it can be equal, and they're a subset of each other. So a big thing about this class is to use logic approach, right? To really understand and solve the problem using logic. And in programming, we use the same approach to apply logic to be able to solve problems. Okay. No question? All right, let's talk about union and set operations. So we have set A and set B in our notes. This is on page 3. And we see that there's overlapping, right? Looking at this. So here's A and here's B. So it tells you here that X is an element of A and X is an element of B. So if you have set A as 1, 2, 3, 4, and B is 2, 3, 4, 6, 7, 9, and C is 1, 2, 9, when you have a union, think of a union like a marriage, right? You have one side of the family, another side of the family, right? And when the two get married, right, both sides become family members by marriage. So you combine everybody. But remember that the values are unique, so you don't repeat the values if they're the same on both sets. So this is why we have from A, set A, 1, 2, 3, 4. And then set B, since we already have 2 and 3 from set A, we just add the values that were different from A to the group, the collection. So we have 6, 7, 9. So we combine 2 of the sets and we only keep the unique value. So if it's repeating, we only mention it once in that set. Okay, so when A union B, we have 1, 2, 3, 4, 5, 6, 7, 9. B union C, you would take the values in the B set, and you combine with the C. Since 2 is repeating, we only mention it once. So we have 1, 2, 3, right? The 2 came from both set, the 1 came from C, right? The 3 came from set B. 4, 6, 7, 9 also came from set B. So in union, we combine. And then A union C. So we have 1 and 2 repeating, so we only mention it once. So 1, 2, 3 came from A, 4 came from A, and 9 came from C. Important things to note here is this. It says that for any set S, S union empty set is S, right? So when you have a set and then you have an empty set and you have a union of those sets, you have the original set. S union universe is the universe. Okay, so let's do set operations for 11. So I have X is 10, 20, 30, 40, 50. Y is 30, 40, 50, 60, 70. And Z is 10, 50, 100, 200. So first we're gonna do A for number 11, where X union Y. So if we're looking at this set combined with this set, right? So we start with 10 from X, 20 from X, 30 in both, so we only mention it once, 30. 40 is also in both. 50 is in both. 60 came from Y, and 70 came from Y. So that would be the output for the union of set X and set Y. Then for B, we're going to do X union Z. So X and Z has 10, right? Because we combine them, we only mention it once, so we need to put it down once, 10. 20 came from X. 30 came from X. 40 came from X. Since X and Z have 50, we only need to mention it once, so we just need to bring 50 down. And then don't forget about the 100 and the 200 came from Z. So you combine these, so any repeating number, you're only going to need to include it once. And same process with Y union Z. So when we're looking at Y, we start with 30, Z, we have a 10. So bring the 10 down. I keep it in order so that way I can, you know, keep track of the number so it's easier for me, right? So technically set SCL and C++ has that pre-sort, the weeks ordering, but you can have it in unordered, that's fine. It's just easier for me to track the numbers that way. So I brought down the 10 from Z. And then since we're combining, we gotta also bring down the 30 from Y. And then the 40 from Y. They both have 50, so we bring that 50 down. 60 from Y, 70 from Y, and the 100 and 200 from Z. So that's the output for when we union Y with Z. So for quiz and test, we need to know how to do union operation for sets. Any question? No question for 11. Okay. Going back to notes. Let's talk about intersection. So in this Venn diagram, we see that we have set A and set B. Now we are going to look at the only overlapping population here. The values are overlapping between these sets. So that will be our intersection. Okay. So we said that X is an element of A and X is an element of B. So given that A is 1, 2, 3, 4, B is 2, 3, 4, 6, 7, 9, and C is 1, 2, 9. So when we're looking at the intersection, we're going to identify the numbers that appear in both sets, such as 2, 3, and 4. 2, 3, and 4 appears in A, and 2, 3, and 4 appears in B. So that those are the intersection values. So that's what you include here. So for intersection, we only identify the numbers that appear in both sets. For B and C, we see that 2 appears in both B and C. 9 appears in both B and C, and nothing else, right? Because 4, 6, 7 doesn't happen here, doesn't appear in C. So 2 and 9 for intersection BC. When A intersects with C, when you were looking at A and C, we see that 1 appears in both, 2 appears in both, and that's it, because 3 and 4 is not here, and 9 is not there. So we would have 1 and 2 as A intersection C. And again, important to note that when you have any set S, set S intersects with empty set is empty set, and S intersects with universe is S. Okay. And then it says that when sets A and sets B are disjointed, if and only if A intersects with B is an empty set. So if it's completely disjointed, there will be no intersection, and that will be an empty set. No values would be intersecting, would be the same in both sets. Okay, something else that's also added here. It says if A and B are finite sets. The cardinality of A union B is given by A union B is equal to cardinality of A plus cardinality of B minus A, right, intersection B. So you're looking at the number of elements from A and the number of elements from B, and then you also subtract the elements that are overlapping or intersection of A and B. That would give you the cardinality of A union B. Okay? Okay, so let's do the next one on our exercise so you can get some practice. 412. When you have R is 5, 10, 15, 20, and 60, S is 10, 15, 25, 35, T is 15, 25, 35, 45, and 60. First, we're going to do R intersection S. So when you're looking at R and S, what numbers appear in both sets? We have the 10, because 5 only happens in R, right? 10 appears here and here. Then we have 15 appears in both sets. The other ones are not. So 10 and 15. Next, we're going to do S intersection T. Looking at this set and this set. So we saw that 10 only happens in S, but 15 appears in both S and T. So we have 15. Same with 25. 25 happens in both. It appears in set S and set T. And 35 appears in set S and set T. We can eliminate 45 and 60 because that only appears in set T. So our intersection for S and T, that will be 15, 25, and 35. We repeat the same process for 12C. We have R and T. So we can eliminate 5 and 10 because those only appear in set R. We can put down 15 because it appears in both. 20 only appears in R. Same thing with 25, 35, and 45. We don't include those because it only appears in T. But 60 appears in both sets. So 15 and 60 for the intersection. Any question? So you're expected to know intersection for quiz and exam as well, along with union and set builder notation and Venn diagram.
I have a question.
Sure.
For the unions, you wouldn't include multiple instances of the same number?
No.
Okay.
Yeah, they have, if they're the same in both, and when you combine them, you only mention it once. Yeah, you don't repeat the same number. And you see that in the C++ side that they are unique. So you cannot have a duplicate number. You cannot have a duplicate number. Other questions? Okay. I'm going to switch back to notes now, okay? So here it talks about principle of inclusion and exclusion, and we will also revisit this when we're looking at probability, because in order to determine some of the probability, you have to include or exclude certain subset. So we'll come back to this, but for now, it says that the principle and the principle of inclusion and exclusion, when you add up the cardinality of set A and set B, we counted all the elements in the element A and B. But we also include, right, the intersection twice because it's overlapping, right? Remember the last question you just asked me that we don't include the repeated numbers, right? So if we don't subtract this part, what happens is you actually include it twice. So you have to subtract it to get the actual number of elements that will be part of the two sets in union. Okay. So we have to subtract the intersection size, the number of elements that intersects. So remember how we're looking at each of the value? Some have 2, some have 3, some might even have 1. So you have to subtract the cardinality. Like if it has 1 intersected, then it's 1. If it has 5 intersected, then it's 5, right? So if my set here is 10 and my set here is also 10, I have 20. And if it intersects 5, then I would take 20 minus 5, which gives me 15 for the cardinality size of the union of A and B. Okay. Any question with principle of inclusion, exclusion? And we'll come back to this a little more when we apply additional concepts to it, okay? So now we're going to talk about complement. Because you already learned about 2's complement, and 1 complement from your lab last week is doing the till, and then the lab before that you did the 2's complement. But let's look at sets now. So you can use the little line on top of the letter to indicate complement of that set. Okay, so here it says that X is an element of the universe and X is not an element of A. Okay, that means that it will be anything but A. Okay, it's everything red here. It's not inside A. So it's like saying this. Some of you did this last week when you were programming the condition in the loan application or the insurance discount. Like I gave you an example, right? I said when you have a variable is not equal to 0, what could it be equal to, right? So if you have int variable 1 is not 0. If it's not 0, it could be any other number, right, in that universe. So it could be any other number in the integer set. 1, it could be 100, it could be 5,000. If we didn't use the unsigned, then it could be -5, right? So if it's not in A, then it's everything, it could be anything in this universe here, right? All right, so remember inclusion, exclusion principle. So we have set A is 1, 2, 3, 4. B is 2, 3, 4, 6, 7, 9 again, and C is 1, 2, 9. Here's our universe. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So when you're looking at the complement of A is 0, 5, 6, 7, 8, 9. Why? Is that it's everything else except for these number. 1, 2, 3, 4. You eliminate those number and you include everything else in the universe. So it's the difference. Okay, so here's the universe. That's the larger population. And here's A, 1 through 4. Larger population, 1 through 4. So if you exclude A, then you have everybody else. So the complement of A is exclusion of A, and that's everybody else in the universe. So you have 0, 5, 6, 7, 8, and 9. Okay, what about B? Here's B, 2, 3, 4, 6, 7, 9. Here's the universe, 0 through 9. So when you compare B to the universe, right, what's the difference? Well, B doesn't have the 0. It doesn't have the 1. It has the 2, so we can't include that. 3, no. 4, no. It does not have 5, so 5. It has 6, 7. It does not have 8, so we put 8. And it has 9. So our result for complement of B is 0, 1, 5, and 8. So we simply take the universe, exclude the numbers from B, and that would be your complement of B. For C, C has 1, 2, 9. So we exclude this number, so we would have 0, right? We exclude 1, 2. We would have 3, 4, 5, 6, 7, 8. We don't have 9 because 9 was part of C. Okay, so basically we look at the difference compared to the universe. So it says that the empty and the universal sets are related. The complement of the empty set is universe, and the complement of the universe is the empty set. So let's go and do our complement of 2 sets, X, actually 3 sets, X, Y, and Z. Let me move this down for number 13. So we need to find complement for X, Y, and Z. X is 20, 30, 40, 45. Y is 25, 30, 40, 50, 55, 60. Z is 30, 35, 50, 55, 65, and here's your universe. So we can do a complement of X compared to the universe. So the universe has 10, right? So we exclude 20 because 20 is in X. We would put 25. That's not in X. We don't include 30 because that's in X. We would put 35 because 35 is not in X. 40 is in X, so we don't include 40 in our answer. Same with 45. And then 50, 55, 60, 65, 70, 75, and 80, we include those because X ends at 45 there. So we look at the difference compared in the universe compared to X. So if it's in X, we don't include those. Okay. So that's a complement of X. And then the complement of Y. So here's Y. And you need to compare that to the universe. So the universe has 10, Y doesn't, so we put 10. The universe has 20, Y doesn't, so we put 20. Y has 25, so we cannot include 25 in our answer here. So no 25. No 30, because Y has 30. We can put down 35 because Y does not have 35. 40 has Y, so no. 45, we can put down 45. Y does not have 45. 50 and 55, Y has both of those, so we don't include those, along with 60. So 50, 55, and 60 we cannot include. But Y stop at 60, so we can include 65, 70, 75, and 80 in the result for the complement of Y. So now you need to do on your own complement of Z. Look at the Z set, compare that to the universe. The values that's not in Z, but in the universe, you would include in your complement result. Any questions? So I'll give you a minute or so to finish Z complement. Make sure we periodically save our work if you're typing it. So that way, in case you lose power or something, you don't start all over again. Okay, are we okay with 13? Yes? All right, let's move on to difference now. So earlier, just now, we just did the complement where we're looking at the set compared to the universe. Now we're going to look at two sets and find the difference between these sets. Okay. So if we have X is an element of A and X is not an element of B, right? That means it's in the red right here. Okay. It's not in B, but it's in A. It cannot be in the overlap here because that will be in B as well. So it only could be right here in the red. Okay. So what we need to do is we need to determine the difference. So if we have A, again, it's 1, 2, 3, 4, and B is 2, 3, 4, 6, 7, 9. C is 1, 2, 9. So if we're comparing with A and B, we want to see the difference between the set A and set B. Similar to what you just did right now, right? You, instead of comparing to the universe, you're going to compare one set with another set. So you would only include the number that's going to be unique in the comparison. So you would have to say, okay, is 1 in A and B? If it's not in the other set, you can include it. So A is different because it has 1. So we put 1. 2, we cannot include because they're in both sets. That will be overlapping right here. So 2, no. 3, no. 4, no. Okay. But in this case, we're comparing A to B. We're looking at the difference from A to B. So when you do A subtract B like this, you would only include the value that's in A and that's not in B. We don't do 6, 7, 9. Okay, that's the other way around. So we'll get to that. So in this answer for A minus B, set A minus set B, you would only have a 1. Okay, the only difference is 1, the element 1, because that's the main difference from A to B. Now, when we're looking at from B to A, going the other way, so what we ask is, what's different between set B to set A? So we know that 2 and 2 is the same here, 3, same, 4, same. But 6, 7, 9 is in B and it's not in A, so we can include 6, 7, 9. That's the difference in B. Okay, so B minus A is equal to 6, 7, 9. A minus B is 1. Set of 1 right here. Okay. Then we would look at B minus C. So you're going from B to C here. So we know that they both have 2. That's the first number here. They both have 2. They don't have, the C doesn't have 3, 4. So you can put 3, 4. C doesn't have 6 or 7. But C has 9, so it would be 3, 4, 6, 7. Because B has this value and C doesn't. Okay. Question. Okay, now going back from C to B. So you know that 1 is in C, but it's not in B, so there's 1. 2 is in both, so we cannot include 2. 9 is in both, so we cannot include 9. So there's only 1. 1. And we can continue the process, right? Like A subtract B. Okay. So, I mean, A subtract C. So you would have A, you have 1, 2. It has 1, 2 here. You can have 3, so bring 3 down because 3 doesn't exist in C. 4, 4 is in A but not in C, so 3, 4. And then, yes, question? No question? Okay. So when we go in reverse, C subtract A, we know that they both have 1, so we cannot include 1 in our result. They both have 2, so no 2, right? But from the next number in C is 9, so you have 9. Is it in A? No, so you can have 9. 9 as a result for C minus A. Okay? Okay, so let's do the next one. 14. So you're given A is 2, 4, 6, 8, 10, and B is 4, 5, 6, 7, 8, and C is 1, 3, 5, 6, 7, 8, 9, and 11. So first we're going to operate A minus B. So let's start with the first number. A has 2, B doesn't, so we put 2. A has 4, B also has 4, so no. A has 6, B also has 6, so no. A has 8, B also has 8, so no. A has 10, B doesn't have 10, so we put the 10. So 2 and 10 for A minus B. Any question with that? Okay, number 14B. So next we're going to do set B minus set C. So set B starts with the number 4. Compared to set C, there's no 4 in C, so we put a 4. Set B has a 5. There's a 5 in C, so no. 6, there's a 6 in C, so no. 7, there's a 7 in C, so no. 8, there's an 8 in C, so no. So we stop there, and so we would only have 4 as the result for B minus C. Okay, question? Okay. So again, we can do A minus C. So looking at A compared to C. So A has a 2, C doesn't, so we put a 2. A has a 4, C does not, we put a 4. A has a 6, there's a 6 in C, so no 6. A has 8, C also has 8, so no 8. A has a 10, C doesn't, so we put a 10. So our output for that would be 2, 4, 10. Question? Okay, so you're expected to know how to do complements and also to determine the output to the difference between two sets, like what we've been doing for quiz and exam. Okay, so let's get into the specific type of differences. So symmetric difference. It would indicate with the triangle or delta. So we would have A delta B. So we would have X is an element of A, and X is not an element of B. X is an element of B, and X is not an element of A. So it's saying that X could be in the red area here for A, or the red area here for B. It's never overlapping. This is considered symmetric difference for the sets. So again, we're using the same number for the sets. So you have A is 1, 2, 3, 4, B is 2, 3, 4, 6, 7, 9, and C is 1, 2, 9. And this is on page 5 of your notes. So if we have A delta B, when we have the symmetric A symmetric difference with B, then what we want to do is we want to compare and bring out both differences from both sets. So we first look at the value 1. 1 is in A but not in B, so we note 1. 2, it's in both, so we cannot include 2. 3 is in both, so we don't include 3, so no 3. 4 is in both, so we do not include 4. But in the symmetric difference, you also include the other values in the other set. 6, 7, 9 is in B, but not in A, so we would write those down. 6, 7, 9. So compared to the last exercise that we did, we're only looking at one direction from one set to the next set. In this case, we're looking at the differences in both sets. So we would have 1, 6, 7, 9. So therefore, when we're looking at the symmetric difference between A, B, and A, it would be exactly the same, 1, 6, and 7, 9. Okay. So if we look at 2, 2 is there, 3 is there, so no, 4 is there, so no. But 1 is in A and not in B, so 1, 6, 7, 9, so exactly the same. Okay, let's check one more like B, symmetric difference with C. So if we're looking at 2, 3, 4, 6, 7, 9 compared to 1, 2, 9, so we know that 1 is in C and not in B, so we put 1. Right, 2 is in both, so no. 3 is in B and not in C, so we put 3. 4 is in B, we put 4. 6 and 7 is in B, but not in C, we also put those, 6 and 7. 9 we don't, because 9 is in C. Hopefully I don't lose signal here. Any question? No question? Okay. Let's do the next question in our assignment. 15. So we're given D 1, 3, 5, 6, 7, 9, and 11, and E 2, 4, 6, 7, and 10, and F is 3, 4, 7, and 12. We need to find a symmetric difference between D and E. So to start, D has 1 and E doesn't, so we put 1. E has 2 and D does not, so we put 2. D has 3 and E does not, so we put 3. 4 is in E and not in D, so we put 4. 5 is in D and not in E, so we put 5. 6 and 7, these values are in both, so we don't include those in the answer for the symmetric difference. 9 is in D, but not in E, so we put 9. 10 is in E and not in D, so we put 10. And 11 is in D and not in E, we put 11. So that's our output for 15A. Okay, any question? Okay, I'll try to wrap everything up soon. So again, we would do for B. So this time we would do set E and set F, find the symmetric difference between those sets. So set E has 2 and F doesn't, so we put a 2. F has 3 and E does not, so we put 3. E has, well, they both have 4, so we don't include 4. So no 4 in our answer. For 6, 6 is in E and not in F, so we put 6. 7 is in both, so we don't include 7 in our answer, so no 7 here. 10 is in E and not in F, so we put 10. And then F has 12 and E does not, so we put down 12. So it's 2, 3, 6, 10, and 12. And you need to do C on your own. Find a symmetric difference between D and F, and you would start with the 1 there. So write down the result for 15C. Oh, I only have a few more to go, so we can do it in about 10-15 minutes. We might go over a few minutes, but any question with symmetric difference? So make sure you know how to determine symmetric difference between the sets. Here, there's some additional information about looking at the sets, using the set notation. So let's talk about power sets. So if A is a set, then power sets of A is P of A. And that means that it would be the set of all subsets. So when you have like 1, 2, 3, 4, 5, all of those individual value can be subset of that larger set. Okay? So when we're looking at A has 1 and 2. Then P of A would include empty set, set of just 1, set that would contain 2, and then 1 and 2. So these are the subset within the larger set. So I would have an empty set of one element, which is 1, set of another element, which is 2, and then another subset that has 2 elements, which is 1 and 2. So it says that the elements of P of A are sets, not numbers. In general, the cardinality of the power set is that it's 2 Yeah, it should be 2 to the power of A. So 2 to the power of A. Okay. So let's take a look at this example. You have set S, A, B, C, D. Okay. You guys see my screen okay? I just want to make sure.
Yes, Professor.
Okay, good. Okay, I just want to make sure because sometimes, you know, if I keep on talking and then if I lose signal or something, I'm just talking to myself. All right, so we have set A, B, C, D as part of S. So you would start with the first 0 element in an empty set. So that will be the first. So that is one subset to start. Then you would have one element subset, A by itself, B by itself, C by itself, and D by itself. Okay. Then you would have 2 element subset, AB, AC, AD, BC, BD, and CD. Then you would have 3 elements, ABC, ABD, ACD, and BCD. And then lastly, we come back to 4 elements, which is A, B, C, D. So you always start with an empty set, then you move on to the 1 element subset, 2 element subset, 3 element subset, 4 element subset. Now, in the case where you have 5 or 50 elements in that set, so we have to build out our power sets, right, by including all the little subsets. So altogether, your power sets would be 16 because there are 4 elements. So you would have 2 to the 4 power. That would give you 16. Okay. And a power set of an empty set is an empty set because it's 2 to the 0 is going to give you 1. Okay. So let's power through the next one. I might go over a few minutes, but I know that sometimes they schedule this to 8:05, but here we go. So if we're looking at number 16, given S is 2, 3, 4, you need to determine the power sets of S. So you would start with the first subset, which is an empty set. So you can notate empty set 0. It could be either like this or with it, right? Then you have a 1 element set, which is 2 by itself. That's a subset, 3 by itself, 4 by itself. So that's the subset of these. 2 element subsets, we would have 2, 3, 2, 4, 3, 4. Remember that sets doesn't have to be in order, so just they got to be unique so you cannot repeat. And then lastly, 3 element set, which is 2, 3, 4. That's what we started with. So if you count this up, 1, 2, 3, 4, 5, 6, 7, 8. You should have 2 to the third, which is equal to 8. That should be the same answer as if you use the formula 2 to the n, where n is the number of elements in that set, which gives you the power sets. So if I have 50 elements, that will be 2 to the 50th power, right? Which gives you the value, which is the number of subsets can be established within that 50 element set. That's what we call power set. Any question? Today material is a little longer than last week, but as you go through it, you know, you can go back, look at the example, redo some of the exercise so you can be familiar with it. Or when you do your homework this week, right, you might revisit some of the questions again. Okay. So do you need to see this again? I'll put this up for a little bit and then we'll switch gear to Cartesian. So you should count up the subsets and that should be equal to the number that's going to be 2 to the n, right? So if it's 3 elements, it's 2 to the third, that'd be 8. So you should have 8 subsets.
So if we're used to just using the formula, do we have to write out each subset when we're showing work or no?
No, but you need to understand that that's how it should be broken down to. Okay? Because yeah, that's another way that you can check. But I don't expect you to write out a bunch of subsets if we have like, you know, 50 or 10 or 15. That's too much. But yes, you should know how to apply the formula. Okay, because this is gonna, with Cartesian products, this is gonna lead us into combinatorics, where you're gonna look at the combo with the numbers. Okay. Variations and then going into probability. Okay, so let's talk about Cartesian product. So with Cartesian product is an operation that's going to give us a set or a product set by multiplying the sets together. Like if I have set R and S, I can multiply it together to get another set. Okay. So if we're looking at the actual elements, we would refer to those as how we would write out with ordered pairs. Okay, like how it would visualize on the plane with X and Y on the 2-dimension. So when we do A times B, we would indicate that it's XY, where X is an element of A and Y is an element of B. So when you have A is 1, 2, 3 and B is AB, when you multiply these sets, the Cartesian products is going to give us 1A, the first pair, 1B, the next ordered pair, 2A, 2B, 3A, and 3B. Okay. So in the case where we would have, looking at the ordered pairs, if you have more than 2, like in the case of 3, then it's triple, or what they would say is triptuple, or n-tuple of the n components. Okay, like this would show you 1AX, right? Because X comes from the third one here, and 1AY. So what you do is you switch it up and you would get the combination of the pairs. We shouldn't even call the pairs, but or the three components, and that's going to give you the output of the three sets multiply, A, B, and C. Okay, so we're going to do the next one. So for 17, you have given T is 2 and 4, U is 6 and 8, W is 1 and 3. We need to determine the product for T times U times W. So to start, what we did was we would start with the first number, 2, 6, and 1. That will be the first three components. Then I would do 2, 6, and 3. The next component. 2, 8, and 1. 2, 8, and 3. 2, 8, and 3. Then I finish with the 2, I move into the 4. 4, 6, and 1. 4, 6, and 3. 4, 8, and 3. 4, 8, and 1. And then 4, 8, and 3. And you notice that they have to be unique. They're not repeating. Okay. Any questions with Cartesian product? So with this, you would set up, if it's in pair, you would set up the ordered pair, and you would have the combinations of the pairs, right, for the dimension of that product. So if I have T times U, I would only have the combinations of the two. Okay. But in this case, we have 3, so we would have 3 components with the order. So here the author included how that can, for Cartesian product, it cannot be cumulative, it cannot be associative. Now, in the way that we can look at the representation of sets is that the computer system, instead of, we talked about conversion already, but when we're looking at the sets value, it's just saying like which bit of that value is on and which bit is off, right? So in the case where if we're looking at the universe, everything would be on, but then in our subset, some of those numbers would be on, okay? So if we're saying, here's the universe 0 through 9, but if the 1 value is on, so the first bit for the 0 is off, and then the next bit it's on, because that would be 1, 0, and then 1. When it gets to the 2, 2 is next to 1, so that bit is also on, right? So here's the 0, that's off, because it's not in this set. 1 is in the set, so that's on, right? That's the next one in the universe. 2 is on. 3 S doesn't have 3, so that's off. 4 is off. 5 is on. 6 is on. 7 is on. 8 is off, right? 8 is in the universe. It doesn't have it in S. And then 9 is on. And so that's what it used to denote this set for which value bits is on. Okay, with that, I want to finish up the last one. I'm only going to do A, and then you have to do B and C on your own. So here's our universe, same like what the question, the example question in your book, 0 through 9. And we have set A, 2, 3, 5, and 9. So we know that the first two number, 0 and 1, that's off, so it's 0, 0. When it gets to 2, 2 is in A, so that's on. You have a 1. So the third number is on, so the third bit is on. Okay, the third number in the universe matches with our 2. 3, next one, that's on. Okay, so I'll highlight this so you can see. Okay. 4, it's going to skip that. There's no 4 in A, so that's off. 5, it's on, so 1. 6, 7, and 8, that's off because there's no 6, 7, 8 here, so 0, 0, 0. And then the last number is 9. It's on, so 1. Okay, so you need to do B, and I'll start it off for you. 0 is off, 1 is on, 2 is off, 3 is off, right? 4 is on, and then therefore. Keep going. So skip 5, 6 on, skip 7, 8 on, skip 9. So finish out B and C. Save your work. You can submit it today or 2 days from now before our lab. That's when it's due. Okay. All right, any question? Okay. So if you want to be sure, type your name in the chat. I will pull the Canvas usage and also the participant list from Zoom. But please include your name in case you use a different name on your Zoom login. Like you use a nickname, then I don't know your full name, and then I don't want to mark you absent. So. Okay, so if you want to preview the lab, it should be available tomorrow, I think in the afternoon. You can take a look at it and then, you know, see if you can. We're going to do similar to what we did last week. We're going to create example program or use example program and do some analysis and answer some of the questions. So from here on up, the program does get a little bit more advanced than what we saw last week was very easy. But you can take a look at the lab starting tomorrow, okay? All right, you have any question for me? No question, okay. If you can think of a question later, you can message me or you can check out my office hours or you can ask next time. I'll see you here on Thursday. Have a good night, everybody. Take care.
Good night. Thank you.
You're welcome. Bye. You guys okay? Any question? Okay, I'm gonna sign off if you don't have any question. Okay, bye, Eric. Bye, Lachelle. See you Thursday, okay?